Can you see my slide?
Yes, sir. It's blank though.
Yes, that's the whole idea.
Okay, perfect.
Come on, now you should come up with a question for the exam. I left it blank. Okay, let's start. I believe we are still 1 minute or 2 minutes left. I'm going to just an overview of what we discussed last lecture. We mentioned we have gray and diffuse surfaces. In the diffuse surface, is the physical property is independent of direction. It means it's uniformly distributed in all directions. Therefore, every angle is the same. When we're talking about the gray surface, it means the physical property is of the surface material is independent of the wavelength. Therefore, these are the you have to keep in mind. When we are saying diffuse, it means independent of direction. In the case of gray, it's independent of the wavelength. As I mentioned, if you look at here, this is representing the emissivity of the material. And here the angle, as we change the angle, it means in 15 degree, these are the diffusive value. When we go to 75, the diffusive value will change. In black body, we assume that is independent. There is always constant. The value of emissivity is equal 1. When with the gray surface we're dealing, for example, a given temperature, it's changed a little bit, okay? But always in our calculation, we assume the surface is gray body, and we assume it's almost constant, okay? Here it also shows some different material that we have. I show you this slide before again. We can see here is represent the emissivity. You can see it is a function of the wavelength for different material at different temperature and so on. Therefore, you can see it's 1200 here. For this is a stainless steel. If you go to 800, this become like this. If you go to 200, this is 800, and this is 1200, and so on. Therefore, you can see it's also a function of the temperature and also the wavelength. As I mentioned, for most of the material we're dealing we are dealing in the wavelength with thermal radiation is usually very constant here within this value. Therefore, we can assume between 0.4 to 0.7 or 1 is almost we can assume is constant again in our application. And if you look at here the temperature, we're dealing very low temperature here, ambient temperature 20, minus 20. Therefore, we can assume it's constant. Again, we discussed before what is the definition of absorptivity, what is reflectivity and transmissivity. Because if we have some radiation comes here, G, watt per square meter, you can see some of them will pass through it. We call transmissivity. For some material, we would like this value be high, like a glass. And again, we have portion will be absorbed. For example, for building material, we would like to have some absorbability to store the energy because we don't want immediately the energy to reflect inside. And also we have dealing with reflectivity, for example, dealing with the glasses and so on, we would like sometimes reflectivity and so on, okay? Therefore, these are the three characteristics of the material when we're trying to select for a certain application. And we mentioned absorbability is a portion that absorbs to total radiation. Therefore, here, this portion has been absorbed to the amount of total coming. Therefore, it's a percentage. Therefore, if we add them up, all of them summation has to be equal 1. Because if you write an energy balance, the portion is absorbed, the portion is reflected, the portion is transmitted, it has to be equal to the amount of that is coming here. And if you replace them based on what we mentioned here, absorption is G alpha and so on, the summation become 1. Therefore, this is simply a conservation of energy. The total comes here is equal to the summation of this one. Again, depend on the material we have, this value alpha, rho, and tau will change. For example, opaque surface is material that transmission is equal to 0. Therefore, this summation has to be equal to 0. Again, we mentioned here, depend on application. Application we assume is a function of wavelength, or we assume is independent of wavelength. Okay. In general, absorbability, as we showed in the previous picture, is a function of wavelength. Therefore, for a given wavelength, absorptivity for that one. The same thing, we are talking about reflectivity and so on. Therefore, depend on the material we have, okay? As I mentioned here, we can see the wavelength, absorptivity, emissivity are function of the wavelength, okay? Therefore, here is a function of wavelength, we can see it changing. Now, the average absorptivity, if you would like to calculate what that means, we have to take the integral over the range of 0 to infinity. Therefore, I calculate all the energy had been absorbed from 0 to infinity, the total energy coming, and they define this average. This is the definition of average. The total absorbed to the total received, the total reflected, the total reflect, okay? Therefore, all of them, these are the amount of radiation coming to the system, this portion absorption, reflection, and transmissivity. These are the definitions that we have. Therefore, if you look at the table, show you the alpha, that alpha is the average value, okay? The average value. Again, we have to go back to understand again the part what we mean here. For simplicity, again, for simplicity in our calculation, surfaces are assumed to reflect in perfectly, we call it specular or diffuse. As I mentioned, diffuse, the surface that in all directions are the same. When we say specular, it means that energy comes here, this angle is equal to this angle, reflected back, okay? Therefore, these are the two surfaces. Most of our application, we assume the surface acting as like a diffuse, okay?
Sir?
Yes, sir.
In what case would it be specular?
Depend on application that you have, my friend. For example, okay, depend on what, if you're trying to, again, it's come the characteristic of the material. Okay, we're trying to design a material for certain application. Okay, in reality, is like that, specular. In reality, for simplicity in our calculation, it's act like this.
Okay.
In real application, you can look at the building material may reflect in one direction more than the other one. But here we assume is diffused in all directions. Okay. Now, Kirchhoff law, again, this Kirchhoff law come back 65 times in life. You have that for in the case of application that we have for thermodynamics, for electricity, okay? We mentioned Kirchhoff law, but here we're trying to, this again is simply conservation of energy. Conservation of energy that we call it summation of energy go to that point is equal to 0. The summation of current goes to one point is equal to 0, okay? We're trying to find, because so far we have been able to define a way to find the value of reflectivity, a way to find absorptivity and transmissivity. But now we're trying to define what is the relationship between emissivity and different character, reflectivity, transmissivity, absorptivity, okay? In order to be able to define it, we use this concept that we have a black body here at the temperature of the T. And we place another surface here, we call it AS, okay? Inside that system. And leave it for a long, long period of time. Therefore, this surface of AS that we have is at the temperature of T is start to emit energy, and so there will be energy exchange until reach the equilibrium, okay? Until reach equilibrium. Therefore, we receive a certain amount of energy, and since the temperature will increase, emit a certain portion of energy. Therefore, when receive energy, it means alpha, AS temperature to power 4. And when emit back, it means emissivity. Therefore, we can write this simple energy for this system, the amount of the energy received and the amount of energy emitted back. Therefore, the radiation incident on the part of the surface of a small body equal to radiation emitted by black body. This is the black body emitting surface. Therefore, this is total energy come. Okay, receive the temp again mentions reach equilibrium, the same temperature of the T, and start to emit back. Therefore, this is a portion of energy absorbed by the surface. Okay, this amount of energy absorbed, this was emitted by, and this portion has been absorbed. Now, the surface, since it's at reach equilibrium at the same temperature, again, this surface starts to emit back to bigger surface. This is the amount of energy emitted back. we assume this when reaches equilibrium, the amount of the energy emitted by this small surface is equal to the amount of the energy absorbed by small surfaces. Therefore, if we put these two equations together, we can see simply that alpha is equal to epsilon. We can consider this is equal to this one. Therefore, this is if we use this concept of Kirchhoff law or summation of energy for that surface or energy balance for a small surface to get this conclusion. Therefore, we always find a value for alpha. Therefore, the alpha is equal to the epsilon emissivity of the material. Okay. Therefore, absorbability is equal emissivity. Now I have one simple problem for you to do it. And again, this has come back from, we had it from simple concept of radiation. Consider an opaque horizontal plate. Opaque, what that means? It means transmissivity is equal to 0, right? Is well insulated on the edge, therefore there's no heat transfer from the edge of the surface, and lower surface in the back. The plate is uniformly radiated by from the wall air at the 300 degree flow over surface. Therefore, we have a plate. Therefore, underneath is insulated. On the top edge is insulated only from upper part. And the temperature of the air is around 300 degree, providing a uniform convective heat transfer coefficient for that one. Therefore, heat transfer coefficient from the upper surface is around 40 watt. Again, we're making assuming this under steady state condition, the surface have a radiosity of 4,000 watt per square meter. And the plate temperature is maintained uniformly at 350. Therefore, the air is at 40 degree, at 300 degree, but the surface of the plate is around 350 degree. If the total absorbability of the plate, to total it means in range of the wavelength is 0.4, we're trying to calculate how much radiation emitting from the plate. Therefore, read this problem. There are some vocabulary here that I would like to get to know you, what that means, radiosity. Okay, the surface have a radiosity of 4,000 watt per square meter, what that means. And then it mentioned at the end, determine a radiation on the plate, what that means. Okay, read this question first, trying to understand the vocabulary, trying to understand what is the question, and then we go slowly through it to find out what exactly is asking. I believe it's from your textbook, problem 94. Read it one more time, please.
Sir?
Yes, sir.
So is the radiosity the amount of energy transferred through radiation only?
It's by radiation, but what that exactly means, what is representing, okay? That's you are correct, but what is the value, how we can calculate the value? Okay, good question. Let's go to the next slide. Radiation intensity, okay? Surface emit radiation as well as reflecting. Therefore, whatever surface that you have, there's energy emitting from that one portion is because of reflection, the other portion is because of emission. Therefore, every surface when it's exposed, you have two components from that surface. One is emitted because the surface has a certain temperature, and also because of some radiation comes in, probably this portion will be reflected, probably very low or very high, depending on the reflectivity. Therefore, surface emit radiation as well as reflecting it. Therefore, we have to keep in mind every surface has two simultaneously, emitted and reflected. The total living surface consists of emitted and reflected one. here, okay? Your radiation comes here, this is G, a portion will be reflected, and that's rho G, and a portion is emitted because of the surface of temperature is at T degree. The total of this two component called radiosity. Therefore, radiosity is defined here, J. A portion is emitted, we can calculate emitted because we know the emissivity of material, we know that's one. And also we know how much energy comes here, how much is radiation times reflectivity. Reflectivity could be 0 or maximum 1. Therefore, this portion outcome. The summation of these two components, we call it radiosity. Any question?
Did you say the summation or the difference?
The summation.
Okay, okay.
Summation of this plus this one. Here I mentioned G is radiosity, E is emitted, and G here is reflected, is rho G, because here the amount of radiation hitting this surface. And then a portion will be reflected. What portion is rho G? Now, I have one question from you. If I assume this is a black body, what will be? If I assume that this is a black body, what would be the radiosity?
Shouldn't be 0?
Read this statement here.
It would be equal, no?
Yes, radiosity, if it's black, amount of reflection is 0, because that was the definition of the black body.
Okay.
The black body absorb all the radiation, the temperature will increase and emit it back. Okay, for a black body, radiosity equal to emissive power, this one. Okay, therefore for black body, G equal EB, because we assume there's no reflection, because we assume absorb all the radiation. That's the definition of the black body. Alpha is equal 1. Right, my friend? You agree?
Yeah.
We have to go back and slowly bring those information that we have. We define a black body is a body that absorbs all the energy. It means absorbability is equal 1. Alpha is equal 1. Now, remember we mentioned alpha plus rho plus tau is equal 1. Therefore, no transmission, no reflection. And therefore, in case of the black body, J equal this one. This term is equal 0. Good. Let's go back to the problem that we had before. Now we have consider opaque horizontal plate that's well insulated. That's good on the edge and the lower back. Then back, the plate is uniformly irradiated from the above wall air at the temperature of this one flow over this one. Therefore, the temperature of the air over the plate is 300 degrees, providing a uniform convective heat transfer here. Therefore, the convective heat transfer between the surface and air is around 40 watt per square meter. The surface has radiosity of this one. Now we know what that means, radiosity. And the plate temperature is maintained uniformly at this one. If the total absorbability is equal emissivity, remember again here, is 0.4, determine the irradiation on the plate. How much is G is coming to the plate, okay? Now, read this problem and trying to see, okay, what can I do with those all in this information that I have? They tell me about the convective heat transfer. They gave me the temperature of the air, and they gave me the radiosity. And now they're asking me the total reflectivity. Okay, the first part here is irradiation on the plate. How much radiation comes to the plate? How we can solve this problem?
We need to know the emitted amount.
Say it again, please.
We need to calculate the emitted amount.
Yeah, the question here is, we have to draw the system to visualize it, and then mention, okay, now I'm trying to calculate how much radiation coming on the plate, okay? How can I do that? Therefore, I believe the first point here, I have to write a simple energy balance for the surface of the plate. And trying to consider all the component is contributing to that one. convection, radiation, and so on. And then if I write the simple energy balance, therefore I can see there has to be some energy coming to the system, okay? Therefore, let's go back again. Understand that radiosity. Radiosity is the total emitted, this part, and reflected. Emitted and reflected. This is G, called this, summation of these two called radiosity. Let's look at the problem. Oh, I'm sorry, I gave you all the solution. Therefore, what I have to do, I have to write a simple energy balance. Some energy comes here, G, this is G is coming here. And if I write energy balance for this one, I have some radiosity here. This is summation of reflected and emitted. And there's another term involved here, that's convection. Therefore, this G, radiation comes to the surface, has to be equal to radiosity plus convectivity transfer, okay? That's exactly what we're writing here. Any question on this part? There is a certain amount of energy comes here. The surface of the plate is increased to 350. Because of the temperature difference I have between here and there, I have some convective heat transfer and also some radiation going back. And this is a summation of two components. One portion is reflected because of this, and one portion is emitted because of the temperature difference. Therefore, the simple energy, when G is coming here, is plus radiosity. I can simply write this one is emitted and reflected. Okay, I can write the two terms, but he asked me, he gave me this summation of these two already, okay? Plus a portion is also convected to the environment. And the convected environment is simply H times this. This value already given to me, because it mentioned the radiosity is around 4,000. They gave me what is value of H. I know the temperature difference. Therefore, the total radiation coming to the surface, that G, come here, is around 6,000 watt. Any question this part, please? Do you want to go back to look at the problem again? Now he's asking us, okay, we calculate, it mentioned again, read the problem. We have a temperature difference, we have convective heat transfer, and we know that has a radiosity. He mentioned this is how much energy reflected plus emitted, okay? Therefore, we wrote a simple energy balance, and we were able to find how much radiation actually come to the surface, okay? Mention also find the reflectivity of the plate and emissivity, okay? Again, you have to, we go back, trying to understand the problem. It mentioned already to us the reflectivity, the absorptivity is 0.4. This is a portion of the information is given to us. But also at the beginning, it mentioned the surface is opaque. What that means? Opaque, it means the transmissivity is equal to 0. Therefore, we know the transmissivity is equal to 0. We know absorptivity is 0.4. And also we can write that equation that we have alpha plus rho plus tau is equal to 1. Is opaque, it means transmittivity is equal to 0. Therefore, that's exactly we wrote here. The summation of these three has to be 1. This is because of the conservation of energy. We wrote this equation based on the conservation of energy. We mentioned this is opaque, this equals 0. We know absorptivity, therefore we can calculate reflectivity. Okay?
Sir, could you repeat what is tau again?
It represents the transmission, how much energy is transmitted through the plate.
Okay, thanks.
Sir?
Yes, sir.
So rho G is reflectivity, right?
Rho is reflectivity.
Okay.
Here is, we have this rule here, alpha plus rho times transmissivity is equal 1. In this case, we mentioned the absorptive material. It mentioned that we know this value. It mentioned that is opaque. When it's opaque, tau is equal to 0. Therefore, this becomes 0. We know this value. We can calculate reflectivity. Okay, I will leave the problem here. You should go and read it again because there's some new concept that you should look at it. And I go to next problem, okay? Trying to understand again, we had it in building science that we have this rule we discussed in building science. This came based on simple energy balance of the system. The total energy comes, a portion will be absorbed, a portion will be transmitted, a portion will be reflected on that one. Let's look at this problem, then we go back to that one again. Go back, read the radiosity, and then we come back and do that again, okay? Now, look at this problem. It's a simple idea. The air temperature on a clear night is observed to remain at 4 degrees. Okay. Water is reported to have frozen that night due to the radiation effect. The air temperature is 4 degrees, but we have the water has been frozen. Take the convective heat transfer coefficient to be 18 watt per square meter. Determine the value of the maximum effective sky temperature. This is actually happened. Sometime during the night, the water can be frozen, even the temperature is above 0 degree. Now, what we're trying to do, the air temperature on a clear night is observed to remain at 4 degrees. Therefore, we have a water outside. And when we wake up, we can see is the water is frozen. We look at the weather, we said the temperature of the air is 4 degrees. The question here is how on the earth the water can be frozen when the temperature of the air is around 4 degrees. How can you explain this one to me? Read the problem again. It's trying to really understand the physical phenomenon, what's happening, and what parameters are involved, and how can I find the answer to that one? It's not just taking equation. You know radiation, you know conduction, you know convection, you know everything. But now I'm trying to solve a practical problem.
Sir?
Yes, sir.
Is it that the water emitted radiation, so lost energy, and the actual outside layer of the water actually went down to 0 degree because of that transfer of that radiation from the water to the sky?
Okay, how can I solve the problem? He's asking me what should be the temperature of the sky in order to this process take place.
Well, we can take the surface of the water at 0 degrees to consider that it's
Write down the equation, sir.
yep.
Please. Any suggestion? Therefore, you take, as he mentioned, write a simple energy balance for the surface of the water. And what form of equation should be that?
We have radiation and convection.
And convection or conduction?
Convection.
Convection. Therefore, you write a simple energy balance for the surface. You mentioned this reach equilibrium at this moment. The temperature of the surface of water is 0 degree, and therefore there is a convection between air and surface of the water. And then also this surface of the water radiating to the sky, losing energy to the sky, because the temperature of the air is 7 degrees, temperature of the water is 0, therefore you are getting energy from convection, and then you are losing to the sky. And the sky here is at what temperature? Therefore you can write a simple energy balance here. This is the convective heat transfer between the air and the surface. And then this is energy gaining from the air, and this energy losing to the sky, okay, by radiation, because here is the water, here surface, and only seeing sky here, okay? Sky, this temperature here. And for this, write a simple this energy balance. And the question, what is emissivity? Here we assume 0.95, okay? And based on that one, we can calculate. And if the temperature of the sky is around 254 and minus 20 degrees centigrade, therefore we can have a frozen ice in the morning, okay? And that this was technology was using many thousand years to make a sky, make ice during the winter time in desert, because in the desert you do not have, you have a very clear sky, there is no humidity, therefore that was the temperature, low temperature that you have, okay? So they're using the sky of temperature and preparing a very thin layer of water here, and during the night and during the day it was ice they were taking and storing it, okay? You can go back and read the old technology. Any question, ladies and gentlemen? Any question? Therefore, again, this is just one overview that we had in building science, just repeating some information to be able to remember what exactly the terminology and trying to understand the physics of the problem. We are dealing in heat transfer, conduction, convection, radiation. These are the three processes involved, but we have to understand how we can integrate them together to solve a problem.
Sir?
Yes, sir.
So we consider that radiation and convection are both the same because we're in steady state?
Because when you have the surface of the water, when you have this ice here, right here, therefore there is no sunshine. This is during the night. There is no sunshine, and therefore the surface of the water is frozen. Therefore we assume it's 0. Therefore we write a simple energy balance here. What are the parameters involved? There is no conduction at this moment. We are talking surface of the water here. We assume the water is 0 degree, and we have convecting heat transfer from the surface of the water to the air, because the air is 4 degree. And the same time we have energy. This is from air to the surface, and from the surface to the sky. Reach equilibrium, it means we can mention energy gain from
Oh, I see. Okay.
convective is equal to this one. This is because the system reach equilibrium, okay?
Okay.
Sir, isn't there a conduction between soil, the ground, and water?
Well, again, that's why he put a little bit here. He was a creative. He assumed this is a little bit deep here. Therefore, he can assume the temperature here of the water is equal 0. The water body here is 0. you're not writing the whole energy balance of the system. You're writing only energy balance for the surface.
Okay.
Again, these are very good questions, sir. You mentioned it, but also we have to also consider, in reality, you need some energy for phase change from liquid to solid. But at this moment, it assumed that is already frozen, therefore it does not consider the energy of that part. Okay. Therefore, whenever we are trying to solve a problem, we have to specify the condition. We assume it's already ice, therefore we write this equation. Now the question, if I ask you what should be the temperature and also trying to integrate the time dimension, this equation will not be applied. This equation is only applied when we assume it's steady state and we're writing only the equilibrium energy. Okay, I promise you to go back to do one more problem from chapter 9 because we chapter 9 and then we come.
Quick question, if that's okay.
Yes, please.
I'm assuming this process would work in a dry environment, right? But would it also work in a very humid environment? I don't like. I feel like that would affect it. No.
No, because when we have a very humid environment, you have a lot of moisture in the air, and that moisture in the air acts like a blanket. Therefore, that your sky temperature will be much higher because those humidity are in the air, okay, in the atmosphere, and the temperature is more like a temperature of the air rather than temperature of the sky. That's why in most of the desert area, the people, even during the night, they feel colder than the day, because when they're outside, they're losing energy to the sky by radiation, okay? And therefore but in the colder climate, that will not happen because the temperature of the air is what you feel. But when you are in the desert area, because of the low amount of the humidity in the air and clearness, the sky is very clear, therefore the sky temperature is at around 10, 20 degrees lower than air temperature. Therefore, you're losing energy to the sky by radiation.
Okay, yeah, that makes sense. Thanks.
Sure. Now let's look at this problem. Again, this comes from your textbook, and I would like you to take time and do this problem. Ladies and gentlemen, any suggestion? Any suggestion?
Is it Q equal to Q convection plus Q radiation?
What is the problem asking? It's asking you to determine the temperature of the plate. What are the processes involved here now?
Radiation and convection.
Radiation and convection, but radiation from top or bottom?
From sides?
From both sides, because it mentioned it's suspended in the air. Therefore, we have a plate suspended in the air. We have convection and radiation up. The temperature is 20 for air, and also the temperature of the surrounding, the temperature of this room here is 17 degrees. Therefore, now is exchanging energy back. What is the source of coming? Because it's a resistance. We provide 20 watt energy to this plate. As we provide energy, this electrical heater, the temperature will go up. Okay? Right? Now, the temperature increase, therefore the temperature of the plate will increase, is convecting to the air because the air temperature is 20 degrees and also radiating back to the sky. Therefore, you are right. I write a simple energy balance for this plate. Some energy comes in, 20 watt, and then this energy lost to the environment. There are two components involved by convective heat transfer from the top part and convective heat transfer from the bottom part. And convective heat transfer is H times delta T. I do not know the temperature of the plate, but I know the temperature of the air is 20. I do not know what is the convective heat transfer. And losing from the bottom by convective and radiation. Radiation is, again, here is the temperature of the plate, and we have the temperature of surrounding. Okay, write down the equation, please. The reason I'm insisting that I would like you to see where you are making mistake.
Sir?
Yes, sir.
When you say surrounding surfaces.
So I assume this is, I have this one inside this room and this plate, and here is surrounding, this is the room, the temperature of this wall. Okay, therefore radiation from this plate here inside the room is by radiation between this surface and the temperature of the ceiling and the wall and so on. Okay. Did I answer you, sir?
Yes, sir.
Good, sir.
Sir?
Yes, sir.
We have to calculate the Nusselt number, right?
I do not know, sir. That's why I'm sitting here and drinking my water, and I would like you to give me the solution, sir. I do not know. Write down the equation and the energy balance. First, find out what are the terms involved. Second, identify what information that you have and what information you have to make assumption or calculate. The unknown here is the temperature of the plate. I want to see when I provide 20 watt to this plate and when it reaches steady state condition, what would be the temperature of this plate? And I assume this conduction is too low, the temperature of the surface in the top and bottom is the same. This is an assumption I'm making, okay? Could you please write the equation, identify the parameter, and tell me what should we do? We have almost 2 weeks left, ladies and gentlemen. Wake up and do it, please.
Well, we have to assume the surface temperature to get the Rayleigh number, right?
Please, again, this is your exam. You have to write it down on your paper. Put your idea there. Don't ask me. I will be in Bahama during your exam, okay? Sit down and put whatever you know on the paper and then verify if it's correct, the assumption made you correct or not. Again, something that you should know, because here it did not specify the air velocity. Therefore, you have to assume it's natural convection, and natural convection is for horizontal plate. Okay, therefore you have to calculate this one. And you remember that the equation that you had in table 9.1, okay? You had a graph, if here is mentioning here, it is vertical, if it's inclined, and if it's horizontal, how to define your characteristic length. Okay, this is area, surface area, divided by perimeter of the plate. Okay, therefore this is the equation that you have, okay? I just put it here, it doesn't mean anything, okay? As you said, sir, you are correct. Now we have to calculate the Rayleigh number. Now let's go back. I'm sorry, let me go back again. Now, there was one question one gentleman asked at the beginning of the class. It mentioned now, I have to assume a temperature for the plate. You are right, because you have to calculate Rayleigh number. In order to calculate Rayleigh number, you need the temperature difference between the plate and air. Now, what should be the temperature? Is it good if I assume the temperature is 10 degrees?
No.
Higher than 20.
It has to be higher than 20. Therefore, you can say, okay, any number, you can mention 30 degrees, 40 degrees, 50 degrees, anything, okay? But we mentioned this convection and radiation, therefore this energy has to leave the surface. Therefore, the temperature has to be higher. Let's assume, let's say 40 degrees or 50 degrees, okay? Make an assumption, okay? Therefore, we have to make an assumption because you need to calculate the Rayleigh number, and the Rayleigh number needs a temperature difference. Therefore, we can assume the surface temperature to be 50 degrees. And then now we can assuming, and we have to come back and verify this assumption. And since we are trying to calculate Rayleigh number, we calculated again, table 9.1. All the physical properties are calculated at the film temperature. Therefore, we calculate the film temperature is 35 degrees. Okay. Now, you have this one. Now let's start to do the calculation. You go table A15. Please go
Okay,
there.
so, yeah, so your birthday is coming up November 30th. I'm looking forward to doing this for a long time.
Say it again, sir. Was question or was comment, sir? Okay, now reply. Okay, let's assume now this is, you go end of textbook table A15, and over there, what information that you needed. This is natural convection, therefore we need information about the conductivity, kinematic viscosity, Prandtl number, and so on. Therefore, you go there and look at the table, and these are the numbers you get at 35 degrees. And since you're dealing with the air, beta expansion coefficient is 1 over the TF. Now, again, this is the horizontal plate. When you have a Grashof number, is a characteristic length, LC. And as mentioned before, LC is equal area divided by perimeter, okay? And here, that mentioned here. This one and this one, both of them, because there is no insulation, okay? We have from last year and last one here. So the characteristic length is equal to this one, okay? We have the plate, therefore we can calculate this perimeter and surface area. Okay, this one. Please understand what that means, perimeter, because in midterm, some of you had it really difficult to understand what the perimeter is, okay? This is the perimeter here, this length, plus this length, plus this length, and plus this length. This is the perimeter. Since this one and this one are the same, therefore that's why I mentioned this one plus this one times 2. Okay, please pay attention. That's why I insist put your solution on the paper, because if you understand, if you make mistake, then you can see where is your mistake. Now you have the characteristic length, you have all the physical property, and we've got calculate Rayleigh number. Again, yes, sir.
Why don't we count both sides of the plate?
We're doing both sides of the plate.
Because
Because if you look at the table that you have looking for, the table is easier to visualize it. Good question. Let's look at here, sir. Here you assume for this one, here you assume it's insulated, yes, from here to up there. Therefore, the only exposed area to the up convection, upper part convection is only this area. This area you assume is insulated.
but it isn't our problem suspended in our case?
Then therefore become this case. Therefore, you have to calculate your Rayleigh number for this scenario and this scenario.
Oh, okay. So we divide our thin plate in two.
The thin plate is now the same plate is you're losing to upside and you're losing to downside. Therefore, the correlation that you're using is different. From the upper part is this one, or lower part is this one. Okay.
Okay.
Good, sir. Therefore, here you calculate your Rayleigh number. You know G, as I mentioned, this expansion coefficient for the air. This you calculate 1 over TF. Kelvin, please pay attention. This is Kelvin, it's not centigrade. 35 plus this one. And we assume the temperature of the plate is 50. This is assumption. We have to come back and verify that assumption. And therefore, we have also kinematic viscosity here. Please, please, please remember, again, sometimes you have difficulty to read your own handwriting. This is 2 power 3 and this is 2 power 2. This is the most common mistake students are making in the exam. This is L to power 3, this is kinematic to power 2, okay? Keep in mind, write it down, put in a highlight that you can not make mistake, okay? This is the most common problem the student make in the exam, okay? Therefore, we're going to put this equation. Again, this is a Grashof number times Prandtl number becomes Rayleigh number, this value here. Now you go back, again, it doesn't matter, it's top or bottom, okay? Because Rayleigh number will only depend on this characteristic, not temperature difference. Therefore, based on this number, you can calculate the Nusselt number from upper plate and down lower plate, okay? If you like, if you look at what the top, here, for the top, your Rayleigh number is, I believe it was 10 to the power something. You can find it from these two equations, okay? What was 10 to the power 6 or hello? What was your Rayleigh number?
2.22 10 to the fifth.
Therefore, it's in this range, okay? Therefore, you're taking this correlation. For 2 to 10 to the power 5 is this correlation that you have, okay? And if you look at for bottom part, again, you can this one, okay? Let's go one by one. Again, look at what the top, it is the correlation that you're using. And you can calculate your Nusselt number. Therefore, now you have Nusselt number. Now you have characteristic length. You have conductivity. You can calculate your heat transfer coefficient from the top surface of the plate. And that's the value. Okay. Therefore, now you have this value. This is heat transfer coefficient from the upper part of the plate to the outside. Okay. Therefore, you can simply calculate. Now you have H, you have temperature difference. You can simply calculate how much is your heat transfer from the top. H is this value. You assume the temperature of the plate, okay? But now we have to calculate what exactly it is, okay? Because the whole idea is trying to calculate the surface temperature, okay? Therefore, this is, you can write the general equation, but you do not know the Q, and you do not know the temperature of the surface, because the whole idea here is to calculate the temperature of the surface. So we can write convective heat transfer from the top, convective heat transfer by natural convection. Convective heat transfer to top by natural convection is this one. You know the surface area, you know this one. The only thing you do not know is TS. Therefore, this one, okay? We can do it now, we'll go back, do the same thing. from the bottom of the plate, because now we are assuming also heat transfer down. And in the table that we show you, there is only one equation that's valid from 10 to the power 5 to 10 to the power 11. Therefore, we have only one equation, and we use that equation that we have. Please go back and check and try to write it down. Okay, we go for the bottom, and if you look at table 9.1, you have only one equation from the bottom part, and that equation is like this. Again, the Rayleigh number is the same because the temperature is different, the same, characteristic is the same, the gas is the same, therefore the same value is applied here. And then here it's become this value. Again, we know the conductivity and the characteristic length, we can calculate the Nusselt number right here. The convective heat transfer here, again, for your visualization, for your understanding. Look at here. Remember what was from the top? It was 6.9. If you look at bottom here, is 3.1, okay? The convective heat transfer from the bottom is less because of this phenomena of, because the plate is hot, okay? And therefore this value, we can write it down here, okay? Again, we can write to see how much convective heat transfer from the bottom of the plate. Again, the same equation that we apply here. The only difference here is the convective heat transfer is 3.64. Size is the same. Temperature of the air is the same because it's the temperature of the air from the top and bottom all the same. The air is the same. And for now we have calculated how much energy is lost by convective heat transfer from the top and bottom. Again, the question here is, what should we do next?
Should we take it to our nose?
Now, let's look at here. Look at here again.
Sir?
Yes, sir.
Can we consider the 20 watt from the plate and then top plus bottom equals 20?
Yes, that's absolutely correct. Let's put it here again. It's something you have to look at here. You have to have energy balance. 20 watt is coming is equal energy loss by radiation plus from top and bottom plus Q convection from the bottom plus Q convection from the top, okay? Okay, this is radiation from the top plus bottom. This is the simple energy balance that we have to write down from the beginning. That's why I mentioned put the equation together, because we are writing energy balance for this plate, okay? For this plate. We are providing 20 watt here, again is watt, okay? Okay. And this watt comes here, increase the temperature of the plate. And then we have convective and heat transfer. Convective from outside, top part, and bottom part. We calculated all this one. Also, we have some energy exchange by radiation because the temperature of the surrounding is 17. Therefore, the plate exchanging heat transfer by this surface. Okay, assume the surrounding, it means the temperature of this room here. Okay, assume this plate is inside the room, the room that you are sitting, and the temperature of the walls and ceiling and everywhere is 17 degrees. Therefore, that's radiation. Therefore, we have radiation from the top, radiation from the bottom, convective heat transfer from the top, convectivity. This is the energy balance that we have to write. Again, we calculate how much is what convection from the top. We calculate how much is convection from the bottom. Now we have to also calculate how much is by radiation, okay? That's why I mentioned write the energy balance, okay? Now if you go to this one, any question please? Therefore we did this one. Now we write our energy for also energy by radiation. Again, you're right, we are losing by radiation from the top and by radiation by the bottom. That's why I mentioned twice here. Because the surface area is the same, but we are losing on the top of the plate and from the bottom. That's why we put these two. Emissivity is the same, area is the same, for the top and bottom, sigma is constant. This is the temperature of the plate. We assume the plate is thin and there's no conduction, therefore the temperature on the top and bottom is the same. And here we write the equation here, okay? Now we go back and place all of this in one, the equation that we had before. 20 watt is equal to this plus this, yeah, this one, plus this one, plus the one we had from the top. And from there, we can calculate the temperature. Of course, again, probably you're a little bit shocked here. This is temperature 4. Again, this will not be in the exam, okay? But again, we can solve by trial and error. We find the temperature for the plate. Therefore, we write the total energy is equal from the top, bottom, and radiation. 20 watt, this is energy loss from the top. This is energy loss from the bottom. And this is energy loss by radiation. And if you solve here, this is the only unknown here. The only unknown here is the temperature of Ts. When we calculate the temperature of Ts is around 47.3. Any question? Therefore, my fellow, my friend, my always, yes, sir.
In the previous step, we had the Q bottom and the Q top, and we have two unknowns.
No, we had two unknown because the Q was unknown.
Oh, three unknowns or 4 unknowns, okay.
But now we're replacing the Q, and then this Q top, it was unknown, we replace it here.
Okay, yeah, got it.
Temperature. And for the bottom, we replace the function of the temperature, and for additional function temperature.
Thank you.
No problem, sir. Now, again, we calculate the temperature. We were lucky again. We have to go and buy 649 because the temperature is 43.7 degrees, okay? Therefore, it means we were correct. We don't have to go to verify it again because we assume 50 degrees and 47 is not that much difference. Therefore, the physical property of the air will not change that much by degree of less than 3 degrees, okay? Therefore, we can mention we don't need to verify, go back and recalculate again, okay? You can see, again, you have to exercise, you have to practice. Again, I believe the TR, they're trying to provide you also extra time to help you. But whatever we do, the only time it's useful if you put some effort and try to do the problem yourself, to identify what information is given, what information is unknown, that you develop the procedure to calculate. Therefore, the first thing that you have to do if you're doing an exam, you have to identify this from the first part. Look at here, I'm trying to calculate the temperature. This information was given to me. Now, how can I go and calculate this part, okay? Then you start to use equation. And you identify this in natural convection because we have the temperature difference between the air and the plate. And again, we mentioned the surrounding. Whenever the term surrounding comes back, it means you are exchanging heat energy by radiation, okay? Therefore, you have to slowly put some effort in trying to understand. Again, then it doesn't matter how many problems you solve, exercise. You do only 1 or 2, but you do it all the way to the end that you really understand it, okay? Because some of the students came, I did 100 problems. So what? You did it, but did you do it all the way to the end? You spent some time? Okay, that's very important. Any question, ladies and gentlemen?
Sir, do we neglect the heat transfer coming from the side of the object?
Well, I mean, you can here, if let's go back. Look at here, the word, what that means here.
A thing, like,
Okay, that means you can ignore it, okay?
okay,
That's why I mentioned when you read the problem, trying to pay attention to every word is there, okay? Because that help you to simplify the problem and trying to find an easier solution. Here I mentioned the thin, it means I can ignore the heat transfer from the sides, okay? That's what I mean. Very good question, sir. Any other question?
I do have another question.
Yes, sir.
When we assume the temperature of this thing, we assume it to be 50 degree. So would that matter if we pick another temperature which is higher than 20 degree?
You can assume. Well, I mean that's a very good question. That I would suggest you to do that. You assume the temperature of the plate is 100 degree, and do the same. Repeat this problem again, and to see at the end what answer you will get. If you assume it's 100 degree, assume 100 degree. But when you solve and you find the temperature is around 55 degrees, therefore you say, well, my assumption was wrong. Let me go and do with the 55. Okay. Again, this is a try and error procedure, usually this type of problem. And by doing on computer, it's very easy because you just mentioned add 0.1 degree and until your problem converge. But in general, here you have to, again, trying to a little bit, again, understand the physics of the problem.
Okay, so it's more of like a numerical method, try and error.
A numerical error in the sense of you have only one equation and the temperature T4, and you just put different temperature, you find which one is
right. So the answer gonna converge.
Answer. But
okay.
Again, if you assume 100 degree, and when you solve the problem, and at the end, when you solve 100 degree, at the end you find the temperature is 60 degrees, you think that, then you see your assumption was wrong. Then you go back from 60 degrees, you repeat the problem. Probably get 55, something like that, okay? Therefore, if you start with 100 degree, you will not get 47.3. If you start with 100, you will get another answer, probably around 60 or 70 degrees. And then so what? I assume 100, but it's 70 degree, a big mistake. Then you have to go back and solve the problem based on 70 degree. And after a while, you will see that what you guess and what you get is less than 2 degree, and you can assume, okay, I'm satisfied. Because the physical property of the air will not change in less than 2 degrees or 2 degrees, okay? Did I answer your question, sir?
Yes, absolutely.
Thank you, sir.
There's one more thing doesn't really make sense to me, that is the convection of the two surface, because we use a scenario that one surface is isolated from the bottom or the top. But from my understanding, the question is the object is in the middle, so that means there's heat transfer.
There's no in the middle. I don't know. Okay, let me try to explain it again. Okay,
Yeah.
let me just put it this way. Let me get my glass to be able to see. Very good question, sir. Let me look at here. Okay, sir. Let's assume this is the middle of the plate,
Yes,
right? What is happening in the middle of the plate?
conduction to the surface.
Okay, we assume the temperature everywhere is 20 degree. Here is 20 degree, here is 20 degree.
Okay,
Therefore, if I assume half of the plate here, it means that the center is almost, I can assume, is almost insulated.
It's a mirror.
Pardon me?
We assume the center line of the object as a mirror, and
Mirror, that's right. That's right, exactly. Mirror, it means exactly what it means here, okay? Therefore, exactly is like this here. I can assume, and the top plate is losing. At the center here is, I can assume there's no heat transfer. The center is the same as center as here, and the bottom we are losing heat to outside. Therefore, that's why we use this one twice. We calculate how much heat transfer from the top, how much is transferred from the bottom. Therefore, since we assume it's a uniform plate and there is no temperature gradient in the plate, therefore I can assume the center of the plate is almost, I can assume it's insulated like this, okay? This is the easiest way I can explain it to you, sir.
Okay, thanks.
No problem. Very good. Ask any question you may have asked, because now I can answer it, not during the exam. Any other question, ladies and gentlemen? Okay. We finished chapter 12 almost, but I will come back again to one or two problems to show different application. Because the equation that you know, the terminology you are aware of it, alpha, rho, transmissivity, we know what is the wavelength, we know electromagnetic wave, we know the thermal radiation is a portion of that one. We can calculate how much energy emitted between two wavelengths and so on. Therefore, we went through this process. Now you are familiar with the terminology radiosity, what that means, radiosity means. Okay, therefore these are, again, we had some discussion in building science, but now we are going one step further to solve some different application, okay? Therefore, let me stop here and then let me show you here. The second part that we are going to look at it here is chapter 13. Chapter 13 again is radiation. And look at here the chapter 12, we look at some basic definition of terminology, wavelength, and all this physical characteristic of the material and so on. But we assume that whatever energy emitted from that surface received by other surface. That's why in the problem of the water, we assume the energy comes from the surface of the water will be captured by the sky on the top, okay? That we did, we assume that one. In the case of the last problem, we assume this plate is inside at the room, that whatever energy emitted from this surface will be captured by the surface of the wall. That was a 17 degree, okay? But now there are some scenario that not all the radiation emitted from that surface will be captured by the another one, okay? For example, if you're, again, we go back, getting to that Christmas time, when you're sitting from the fireplace, you're trying to find the best place to get the best amount of energy from the fire. If you change your location, going back and going to the corner, you'll receive less radiation, because all the energy comes from that surface you will not going to receive all of them. You're going to portion of it. Therefore, here we are going to discuss about view factor. As I mentioned before, if you read different textbook, there are different terminology. Sometimes they call it view factor, sometimes they call it shape factor, sometimes they call it angle factor. Therefore, these are the three terminology, or even configuration factor. What they all means here is what portion of energy emitted from that surface reach the other surface. That's the meaning. Percentage. What percentage of energy emitted from surface A will be captured by surface B? And then again, building science, you have seen it. I believe even it was in the final exam, how to calculate the shape factor. But I'm going to go to it one more time to remind you. Okay, develop view factor. Again, define view factor and understanding its importance in radiation, because whenever you write energy balance, you have to correct the correct amount of energy balance, either received or emitted. Therefore, if you make mistake, your calculation will be wrong. Develop view factor relation and calculate the unknown view factor in enclosure. Okay. Calculate the heat transfer between two black surfaces. Okay. Again, we discussed about the energy comes here, emitted. One portion will be received by this surface, portion will be received by this surface, and portion by this surface. Okay. Again, I use that example of you are going to Christmas time. Here is your fireplace. If you are sitting here, probably will receive. If you put your chair just in front of it, you will receive much more energy. But if you put it like this, you will receive less. Okay. Therefore, U factor is purely geometric quantity. Percentage is independent of the surface property and temperature. It has nothing to do with anything of radiation, part of temperature, or characteristic of material and so on. It's only geometric. It's called shape factor in some textbook. In some textbook, they call it configuration factor. In some angle factor, and sometimes U factor. Therefore, all of these four terminology are used to define that one. Okay. Therefore, if you're using different textbooks, you see configuration factor, it means U factor, it means shape factor. Now, what we defined, as I mentioned, is a fraction, percentage. Shape factor of I to J, surface I to J is fractional radiation leaving surface I that reach surface J. Shape factor of this to this one called, for example, if I call this one P, shape factor of P to 3, shape factor of P to 2, shape factor of P to 1. Therefore, this first one is the original surface that energy leaving, and the second terminal here tell me that one received. Energy leaves and received by surface G. And since it's a fraction, it means the maximum can be 1 and the minimum becomes 0. It means in the case of 0, it means no energy has been received by that surface. 1, it means all of the energy. For example, if you're sitting in your room right now, okay, all the energy emitted from your body will be captured by the room. Therefore, in this case, shape factor of body from you to the room, interior room of you're sitting is equal to 1. Because whatever energy leaves your surface eventually be captured by different surface in your room, okay? Therefore, this is the terminology we are using. Again, I'm going one more slide and I will stop. If you look at here, this is the surface that you're sitting there. This is the surface you are, and this is your room. Whatever energy emit from this surface eventually be captured by the surface too. Therefore, the shape factor of 1 to 2 is equal to 1. Because whatever energy leaves here, it will capture by 2. But if you look at the other way, shape factor of 2 to 1 is not equal to 1. Because some energy leaves from surface 2 will be captured by surface 2. If it comes from here, it's here. Therefore, now we can see this one. 1 to 2 is equal to 1, but 2 to 1 is not a 1. Now we're trying to find how we can solve this problem. Okay, if you remember building science, it's called what? Do you remember?
Like a body.
What? No. It was a rule. We call it a rule. There was 2 rules. Those of you remember, there was a rule. We call it what? Reciprocity rule. Remember? Reciprocity rule. And we mentioned F1, 2 times area 1 is equal F21 to area 22. Okay? We will continue this one next lecture. Please start to read. Please start to work hard. My understanding is your exam is December 10th. And there are not many days left. Please start to read. And I believe also the TA is trying to help you. The only time this can help you if you work hard and trying to understand the problem. Have a nice evening. I will be around here for the next 5-10 minutes. If you have any question, please do ask.
Excuse me, sir.
Yes, yeah.
The marker gave back our grades for the part 2 of the project.
Yes.
And he left a couple of comments saying my abstract and my introduction were similar to the first part. But I don't understand why I would lose grades for that because it's the same setup to the problem. So I don't really know how to explain it differently.
Okay, that's very good. I'm sure he has a copy of your report. Just send him an email and ask him, okay, there are some comments here and I would like to know exactly what you mean. Because I honestly, I do not know because I haven't seen the report. He marked it. But if you have any comment or concern or question, please, I believe he mentioned in his email to you that you can contact him back.
Yes, I just want to know, in your opinion, is it valid for us to lose marks in this regard?
This is a very good question. What do you mean valid? If you have not addressed his concern, therefore that's why he did it. But in order to ignore my opinion, but contact him and ask him to clarify and try to explain to him. I'm sure he can understand the situation.
Okay, thank you.
No problem.